The next speaker is Floyd Steen. He will talk about the robust mesh deformation in SU2 using radial basis function interpolation. Floyd first.
Yes, thanks for your introduction, Julio. Hello, everyone. For those who don't know me, I'm Floyd van Steen, and I work as a PhD candidate in the propulsion and power group of the Delft University of Technology. And I know we have already seen a lot of presentations today, but I hope you still have the energy for one more, which is on the topic of robust mesh deformation in SU2 using radial basis function interpolation. So first of all, a little bit about the background. So what's the motivation for doing this? Firstly, within the sense of deforming the mesh, it's important to prevent the effect of having a low mesh quality on your solver convergence. So that's the first reason. And the second is maybe even more important, that within the sense of aerodynamic, within the context of aerodynamic shape optimization, it's important to maintain the largest possible design space. And in that sense, it's important to have a robust mesh deformation method that can deal with all kinds of deformations. However, there are some challenges using mesh deformation. The first can be having small wall clearances and applying large deformations in that area. And to illustrate this, I kind of prepared this simple square mesh which has a red block here in the middle. And if we displace that block downward, you can already see here on the right that near the wall, there's a high skewing of the mesh shells, which significantly reduces the mesh quality. And secondly, we can also have problems dealing with periodic domains. And that can also be illustrated with this figure. If, for instance, this problem is periodic in the y direction, so in the upward direction, you can see that near this periodic domain here on the bottom of the right figure, you can see that there's a high compression of the cells here, which also significantly reduces the mesh quality in that area. And then a final challenge that you could have is that for instance, for viscous flow problems, you would like to maintain the inflation layer during the deformation, as you would like to capture important gradient information in that region. So this is illustrated by these figures, where in this case we have a simple cylinder with an inflation layer, which is then deformed. And if you don't introduce any features in your mesh deformation method, you can see that the inflation layer height is not preserved during a deformation. And ideally, you would like to have a situation like this, where the inflation layer height is being preserved. So in order to do this, it's been chosen to use radial basis function interpolation as a mesh deformation method. Compared to the currently used deformation method of linear elasticity analogy that is being used in SU2, it is very robust, but also very efficient with the use of appropriate data reduction techniques. And then another advantage is that you can modify it to kind of tackle these kind of problems that I've highlighted previously. So let's dive a little bit into the radial basis function interpolation. Basically, it's a point-by-point method which interpolates some surface displacements into the volumetric mesh by using this interpolation function. So it basically states that at any x coordinate, you can find the displacement by summing the interpolation coefficients alpha with a radial basis function evaluation, which is based on the Euclidean distance. You can do this for all control nodes where you have a known displacement, and then you can set up the following system where you have the displacements of your control nodes are equal to some interpolation matrix times the interpolation coefficients factor, where these entries of the interpolation matrix contain the radial basis function evaluations from one control node with respect to the other. Once you've set up the system, you can then solve for the interpolation coefficients, and that allows you to find the internal node displacements by simply evaluating this interpolation functions for your internal nodes. So how do we deal with the problems that I've mentioned before? So for small wall clearances and large displacements, I've implemented a sliding boundary node algorithm, which allows the nodes on the boundaries to slide along with the deformation. And this basically allows you to preserve the orthogonality of the mesh during deformation. And it basically consists of 3 steps. So if this is our initial square mesh with the block in the middle this time, and we have our control nodes that you indicated by the blue nodes. If we first have a free displacement of the sliding nodes based on the block deformation, you arrive at a situation like this. And then basically what you intend to do is that you then project them normally back onto the initial boundary, and that will make it as if these nodes have slid along this boundary, as you can, for instance, see in this area here and over here. And what you can then do is, because you found a new displacement of these nodes, you can then use all these boundary nodes as control nodes for a secondary RBF installation evaluation. And then there's the problem of periodicity. We can actually change the distance functions for which the radial basis function is evaluated. So we can actually make it periodic in a given direction. So for example, in the y direction, we first had that you do it on the basis of the difference between your y coordinate and the y coordinate of your control node. And now you can actually introduce a sign which makes it periodic in a given direction. So in that case, your distance function would look something like this, where you can see the contribution in x, y, and z. And for 2D test case, you can include these figures that indicate the effect that on the support radius. So if it's non-periodic, you have a single non-periodic node with a given support radius of the radial basis function. And if you introduce this periodic distance function, you actually obtain a periodic node pair over the periodic interface. And you can then see that the support radius extends over the periodic interface. So that, basically your domain is periodic in that sense. And the inflation layer preservation also been taken care of. This is done in a similar manner to the sliding boundary node algorithm, where it's basically a free displacement of your inflation layer edge nodes, and then you project them to a certain height. So if, for instance, we have this initial mesh, which consists of a cylinder with some inflation layer edge nodes, you see here in orange. If we displace this cylinder and also deform it, you can find free displacement of these inflation layer edge nodes, and then using the local normal of these wall lines, so to say, or wall elements, you can then displace it back to the initial inflation layer height, and then basically to solve for the deformation in this internal domain, you use the inflation layer edge nodes and your external boundary as control nodes for a secondary RBF interpolation. So in order to keep the methods efficient, computationally efficient, also a data reduction technique is been implemented, which basically uses a reduced set of control nodes to perform the entire interpolation. And this is done by using a double-edged greedy algorithm, which iteratively adds control nodes based on the error, but also on the error direction. So in each iteration, you add the error node with the maximum error, but also a secondary node, which has a difference of a different angle of at least 90 degrees with respect to your first error vector. And then once your tolerance is reached, which is now based on a percentage of your maximum deformation occurring in your domain, the interpolation is performed. So let's look at some results. For this, I've used a 3D conjugate heat transfer test case, which is basically a 3D fluid domain, as you can see here, with 4 equal pins. And I believe this is around 1.7 million elements in this domain. And these pins are subjected to an equal deformation, which was the result from an optimization, which actually failed because the linear elasticity analogy method couldn't deal with the deformations that were occurring in the pins. And therefore, it was really a nice benchmark test case to see how the RBF would perform in that case. And then also for completeness, some settings of the deformation. The support radius was set at 0.005, And the data reduction was the tolerance was set to 1% of the maximum deformation occurring. And you can also see here the deformation that is applied to the pin. So if we have a look at the span-wise minimum orthogonality, which is typically the best indicator of mesh quality, you can see the difference. In this case, I've only included the for the first pin because they were pretty similar for all the pins as they have the same deformation. And for the fluid, you can see that the mesh quality is actually a bit less compared to the linear elasticity analogy. But for the pin, in this case, you can see that it failed at this side of the pin, whereas for the RBF, which is this red one, you can see that it actually stays above 40 degrees, more or less. And if we have a look at this cross-section, sorry, that's too bad. These should have been a bit more high-quality pictures, so sorry for that. But we can still see the effects that I wanted to illustrate. If you look at this cross-section at this location here, you can actually see that for the linear elasticity analogy, there is a very high compression of the cells in the center, which make that method fail for the optimization at least. And for the RBF, you can see that this is not the case and that the minimum mesh quality increased significantly. So, yeah, and then also to show you something about the inflation layer preservation, these are actually both the same graphs, and it's really a shame that the quality of the pictures is not increased. But for this one, the inflation layer is being preserved, and you can notice that at small locations like here, where the inflation layer is slightly bigger than in this location. But it's just to illustrate that this algorithm also works. And then to spice the presentation up a little, I've also included an animation which does work. So yeah, this is the solid pin deformation that was occurring during the deformation. I think this was in 20 steps. So what's next? I still plan to develop further the implementation of the RBF mesh deformation, and it's actually pull request to 240. So if you feel free to check it out. And I plan to also be able to perform this computation using a parallel computation, also with the different algorithms that I mentioned, and also develop a tutorial for any other users that want to use it. And then, more importantly, also the implementation within the discrete adjoint optimization design chain to also evaluate whether this would affect the gradients and how it would affect these gradients, to also see how it performs in that respect. So that concludes my presentation. And if there's any questions, Steen.
Okay, so the floor is open for questions. Yeah.
So the 3D deformation that we showed in your case, it is like the multiple steps that RBF has to do to reach that kind of compression, or is it something that you were just animating to?
In this case, it was for the animation purposes, because for these plots, actually, it was for the pin, it was done in a single step, and for the domain, it was in 5 steps, because in that case, you reach the tolerance a bit sooner, because the deformation you apply in each step is smaller. So yeah, does that answer your question?
Yeah, thank you.
Okay.
I guess what is your distribution of the time variable in the implementation? Is it also an equals or?
In this case, I haven't looked at optimization yet, so that's for the next steps. But it would be an FFT box. Yeah.
Yeah, because I was just thinking like whether you computed the sensitivities using the linear elasticity analogy, but just then apply the RBF marking, but then.
No, it's purely for the mesh deformation so far. So this has actually been implemented in the SU2 def module. So that's basically what it's suitable for at this point. But later on, I also want to try it on the optimization.
Yeah, because I'm wondering whether there's any hindering us to just like implement it and have the add-on pretty quickly.
Yeah, at this stage I don't know yet.
And the pull in the back theory, or it's just mistake.
Sorry.
Always remember that.
Okay. Yeah, sure.
Yeah, I have a quick one. You showed orthogonality comparisons, and that's positive. What about overall cost of time?
Yeah, I was able to run the RBF on my machine, which took on a single processor with I think 16 gigabytes of RAM. It took 10 minutes approximately, and the RBF was run by Prahash very kindly on his workstation, and that took nearly 2 hours. Sorry, the ELA took nearly 2 hours, so it's quite fast compared to the existing methods. But it's depending on what kind of tolerances you use and the test case you're considering. Yeah.
That's it. When you talk about the inflation layers, this is all specified by systems versus something that is
In how it's implemented now is that you implement in or you specify in the config file, you specify the inflation layer height.
Okay, so we are running out of time, so we can thank again the